Okay.
Okay. Good evening, one and all. Myself, Supriya Naika MK, hosting this program. Nothing is impossible. The word itself says, I am impossible. Today we have arranged a special talk on weekday because of availability of eminent resource person, Mr. George Salazar. It's give me a great pleasure in welcoming all of you to the 57th episode of Creative Online Talk. Creative was established with a vision to constructive thinking in various domains. We focus on non-textual, non-academic, non-syllabus knowledge. Creative is a group of curious minds eager to gain new knowledge and working actively in spreading knowledge and creating science awareness. Creative. Cre means creativity, active means activeness. Creative. Creativity with activeness is creative. Sharing of knowledge doubles our knowledge. Knowledge square is our tagline. We organize weekend online talks on every Saturday afternoon on Zoom platform, and we live stream our program on our YouTube channel Creative GBD. Creative is a platform to share discoveries, experiments, innovations, reviews, evaluations with the interested audience. We recognize subject experts and invite them to present their work experiences with us. I thank all our resource persons for accepting our invitations and engaging us with their knowledge. Today, Creative special talk on human space lift challenges to Moon and Mars. To present this, we have a renowned scientist from NASA, Mr. George Salazar, with us today. I feel honored to welcome you, sir, and all the creative volunteers, resource person, and creative participants for this talk. I am sure that you all will feel enriched with knowledge after completion of this event. I welcome you all once again to the program, and I hope you all will have a great time ahead. And I invite Preeti Verghese, creative volunteer, to introduce today's speaker. Over to Preeti. Preeti, unmute yourself.
Yeah. Thank you, Supriya. Thank you. And good evening, everyone. Good evening, sir. So I am Preeti Verghese here. This is just a short bio about our guest speaker of today, Mr. George Salazar. So George Salazar, as my friend said, is a renowned NASA scientist. So NASA stands for National Aeronautics and Space Administration. Just two lines introduction about NASA. NASA is in charge of US science and technology that has to do with airplanes or space. Now, we have Mr. George Salazar between us to continue the guest talk for today. Mr. George Salazar received his Bachelor of Science in Electrical Engineering from the University of Houston and his Master of Science in System Engineering from Southern Methodist University. He has over 39 years of experience in telemetry, communication, speech control, command and data handling, audio, displays and controls, intelligent lighting, project management, and systems engineering, of which he has received various invention patents. He is currently serving at NASA's Johnson Space Center as a human-computer interface technical discipline lead to develop advanced human interfaces to monitor and control spacecraft, as well as serving as the displays and control subsystem manager for the commercial Crew Program and the Artemis Moon Human Lander System. He is a registered professional engineer in the state of Texas. Also, he has Expert System Engineer professional certification through the International Council on System Engineering. It's an immense pleasure to welcome you and to introduce to this program, sir. Thank you. Thank you for giving this opportunity. Thank you, sir.
Thank you, Preeti. So over to you. You can proceed with.
Thank you for those kind words. Thank you for having me. And I look forward to sharing a little bit of knowledge with the audience in terms of what's going to take to go to the moon and Mars. So whenever the presentation is ready, I'm ready to go.
Okay, sir. I think slides are visible, sir.
Okay, I see it now. All right, so the title says challenges to going to the moon and Mars, and I'm going to be primarily focusing more so on the moon because the moon is going to be the key pivotal point, as we call it, in terms of going to Mars. Next slide, please. All right, so this is the discussions that I'm going to be talking about. First, I'm going to give a kind of a brief overview of past and current human spaceflight missions. And then I'm going to talk about the planned human spaceflight mission programs that are on the books for NASA. And then the challenges. The challenges is where I'm going to spend a little bit of time on because there's a lot of challenges that I'm hoping that perhaps folks out there in the audience, students and professors and teachers will be able to participate in trying to help solve those challenges. We have a lot. And so, we need everybody's brain power, if you will, to help solve those challenges. And then conclusion remarks. And I will try to keep this hopefully short so that way I can give them more time for questions and answers. Next slide, please. All right, so first up is going to be past and current human spaceflight missions. So next slide, please. All right, let me just kind of briefly walk you through the human spaceflight missions that NASA has done over the years. So first tab is the Mercury program. So the Mercury program, what was the Mercury program about? Mercury program was basically understanding what it takes to put humans into space. We had no idea of how humans were going to behave physiologically, psychologically in space. So the Mercury program was intended to understand that. And they were all military pilots. And why were they military pilots? Because military pilots, for the most part, understand risk. They understand the risk of flying high performance aircraft. And so, the first set of astronauts, there were 7 in the Mercury program. John Glenn was one of them, as well as Alan Shepard. And it was to understand how to live and work in space. Keep in mind that the Mercury capsule did not have a computer. Back then, computers were almost unheard of. And so what they would do was calculate on the ground trajectory of the spacecraft, and they would send the commands up to the Mercury capsule. Next tab, please. Next came Gemini. Gemini was a big increase in complexity. 2 people could now fly in space. The duration of the mission was longer, and it was to understand how to rendezvous and dock with another spacecraft. This was important for the Apollo space program. Because they were going to have a command service module and a lunar module, and they were going to have to be able to first they're on dock, and then they had to undock so that way they could go to the moon and then come back to Earth. Next tab, please. And then came obviously the Apollo space program, and that was landing humans on the moon. Interesting enough, only 12 people have walked on the moon, and total time on the moon for humans has been about 3.6 days. That's it. So we have not spent a lot of time on the moon. And I'll say a little bit later on about the Artemis program. Next tab, please. So after the Apollo space program, we had the space shuttle program. That's what I started in. And the space shuttle was a major undertaking because it was the first time of a reusable spacecraft. It was 1970s technology, but it was quite complex. The engineers did a fantastic job of developing a spaceship that not only launched like a rocket, but orbited like a satellite, and then came back down to Earth like a jet airplane, if you will. So very complicated system. Obviously, there were some issues. We lost we lost a lot of astronauts on the Challenger, and we also lost astronauts on the other spacecraft that basically broke up in space, Columbia. But we learned a lot about spacecraft. Traveling in space is risky. It's a risky business. Next tab, please. And one of the first stations that we had was, next tab, please. Was Skylab. So Skylab was our first space station. And of course, from the Skylab, we learned a lot about what it took to build a space station. And that's how we have a space station now. Right now, the space station, we're learning a lot about working in a microgravity. Notice that I said microgravity, not zero gravity. I keep hearing the term zero gravity. There's no such thing as zero gravity. There's only microgravity. But there's a lot, that we've been learning about space station, learning how to build reliable systems, learning how the human behaves in a microgravity environment. Next tab, please. And then, of course, now we have, next tab, is a commercial crew program, which I've been involved with. So this is a major undertaking by NASA and somewhat of a shift in terms of how we've always operated. NASA in the past has only done NASA work, but now we're inviting commercial companies. And in the commercial crew program, we have obviously SpaceX and we have Boeing. Next tab, please. And because of that commercial program, the Artemis program is inviting many commercial companies to participate in the Artemis program. Artemis program is kind of like the Apollo space program, but instead of the Apollo space program, which was basically get to the moon and return safely, it is now to send astronauts to the moon and learn to live and work on the moon for a long period of time. This is dress rehearsal for going to Mars. So this is very critical in terms of a space program for Artemis. And so it's not just NASA, but we need the commercial partners. And hopefully India, ISRO, gets involved with that as well. Let's see, next tab or next chart, please. All right, so let's go to the planned human spaceflight programs. Next chart, please. Okay, so basically, here's the phased approach to Mars. Like anything that NASA does, we always think in terms of systems and systematically thinking through a problem. And very similar to scientists, the scientific method, right? Make observations, form a hypothesis, design an experiment, capture data from that experiment, analyze the data and compare against the hypothesis, and then basically iterate as you do it more and more. Same thing with the moon program is a phased approach. First, we have Earth on the left-hand side. And so the Earth program is basically a space station. what does it take for people to live in space for a long period of time? We have, I think it was Scott Kelly that spent almost a year in space, and we learned about how it affected his body, which it was pretty bad in terms of physiological changes to the human body. Of course, as we start going further into space, it's not only physiological, but also psychological, more so. The other thing about the Earth program is that the communications between station and Earth is very short. It's only like 250 milliseconds. Even going to the moon, you see there the middle portion, the moon, the big moon. It looks real big because that's where we're going to learn to live and work in space. That's where we're going to build technology. That's where we're going to learn what works, what doesn't work, how can we improve that. It's important to do that on the moon. Can I get a tab, please? So you see there a bunch of people at the consoles. And so it takes a lot of people to operate space station. Space station has over 350,000 sensors. And so it's, and then over 100 computer systems. And so 4 astronauts or 5 astronauts on space station cannot handle all that. They need the help of the ground control people. Mission Control Center here in Houston, Texas. We also have what we call the Mission Evaluation Room, which basically is a lot of engineers that are supporting the missions. And of course, at least at this point in time, we have the Russians supporting us as well. And so even Earth and even the moon, it's the time duration it helps us basically continue for ground controllers to help astronauts operate not only in low Earth orbit on the Earth, but also as well as going to the moon. Going to the moon, it's probably about a 2-second delay in terms of communications. And so the ground controllers can still help the moon. Now, as we start going to Mars, things start changing drastically because the time delay is now 20 minutes, 40 minutes. It's a long time. So if something bad is happening to the spacecraft or the habitats on the Mars, they cannot depend on mission control on Earth because of the time delays. And so, early on between Earth and the moon, or the low Earth orbit as cislunar space, we can depend on mission control. We can depend on robotics operations, to help the astronauts. As we start going deeper into space, we can no longer depend on it. Can I get a tab, please? So what you're seeing here is that we're going from a crew mission control robotic dependent mission on the left-hand side of that arrow to a crew vehicle robotic dependent type system. In other words, we got to build these systems to help the astronauts because they cannot depend on mission control because we're going further away into space. Next slide, please. All right, so here's the Artemis program, and this is phase 1. Artemis program, as I mentioned, is kind of like the moon program. And so it's a phased approach to basically going back to the moon. And let's see, the first tab, please. So the first thing is Artemis 1. So Artemis 1 is going to be the first human spacecraft to go to the moon in the 21st century. So what does that mean? That means that we're going to test out the systems with no crew on board. This is just going to be a spacecraft by itself. I think we're supposed to launch at the end of August this month or early September. And it's going to launch on SLS. SLS stands for Space Launch Systems. The largest launcher ever built for a long period of time since the days of the Apollo Saturn spacecraft. Next tab, please. And then, if everything works out correctly, we're going to have the first humans to orbit the moon. They're going to be in the actual spacecraft from lessons learned from Artemis 1. And we're going to orbit the moon for a few days and see how the humans interact with the systems, checking out procedures. Procedures are very important in the space program. And then, next slide, please. We're going to launch a solar electric propulsion system. This is going to be critical for Gateway. Gateway is kind of like the space station for the moon, just like the International Space Station is right now. And so right now, this International Space Station is boosted into orbit by the Russian propulsion module. Well, on the moon, for the Gateway, we're going to have a propulsion system developed by NASA called the electric propulsion system. That's going to be the first element. Next tab, please. Afterwards, we're going to have the first pressurized module delivered to Gateway. Next tab, please. Okay, so it's going to be the first pressurized module. And so this is now the beginning, the building block of building a orbiting moon station. And then we have the mission of a human lander system. That's what I'm working on right now, is the human lander system to dock with the Gateway. Well, actually, the first time is not going to dock with Gateway. The SpaceX is developing a human lander system. The Orion's going to dock with the human lander system. And then from there is Artemis 3. Next tab, please. It's going to be a crew mission to Gateway and the lunar surface. And so now the astronauts are going to land on the moon with Artemis 3. And it's going to be the first opportunity for the humans to go back to the moon. Down at the bottom, you can see a lot of activity in terms of what we call commercial lunar payload services. This is where international partners hopefully get involved in developing payloads for doing science experiments, for robotic missions, for habitats for the humans, and all that. So we're trying to engage as a lot of commercial companies and other countries to get involved with the Artemis program. Next slide, please. All right, let's see. All right, challenges. Here's where I'm going to spend a little bit of time because there's quite a few challenges. So the first challenge is obviously the human challenges, okay? So you have the human. There's different parts. First tab, please. The first part, let's talk about the gravity, physiological changes. You got issues with balance disorder, fluid shifts, because there's a microgravity, there's no sinus drain. So if you have, let's say, congestion in your nose, it's not going to drain. It's going to stay in your head. And that's why sometimes you see astronauts' heads kind of bloated. It's because of the sinus is not draining. You got muscular atrophy. What's that? That basically is that your body grows, okay? The body grows about 3% in a microgravity environment. And then you have bone loss. That's critical because bone loss basically means your structure of your body is becoming weaker. And of course, talking about becoming weaker, there's also immune deficiencies associated with living and working in space for a long period of time. But of course, the countermeasures, as we call it, is to do exercise and obviously some medications as well. It's a major challenge. Next one, space radiation. Tab, please. So space radiation is a huge concern. Obviously, the exposure can be basically bad for the astronauts in terms of how much exposure they get to space radiation. And, they can develop cancer. The other thing is because of the space radiation, they can develop what we call cognitive decline. So cognitive decline basically means your ability to think, your ability to problem solve. your ability to understand the situation. That becomes critical because if your state of mind is not right, it's going to be hard to control these complex systems as we go into space. Next tab, please. And then there's isolation and confinement. That's psychologically, or for the mind, a major challenge. Being isolated, being away from your family for a long period of time, working in a team for a long period of time. That's going to be a challenge. You're going to have the challenge of being in a small confined area with a lot of with astronauts, for a long period of time. And so how's your behavior? Think about let's say your brother, being with your brother and sister in a closet, a small little closet, for 9 months or 18 months or 2 years. After a while, you're going to get on each other's nerves, if you will. And so that's going to be a challenge as well. These other psychological challenges, and it's a difficult one because even to some extent, technology cannot help in certain areas. It's something that we need to do more research on, and we are doing some research on it, but I don't think I've seen any definitive solutions for it. Next tab, please. And then, of course, it's the hostile environment. Going to the moon and going to Mars is not like being on Earth. It's a very hazardous environment. Lack of oxygen, high radiation, big temperature swings. These are things that you have to make sure that you're protecting your astronauts for, and so the habitat design becomes very critical. Next tab, please. And then being distance from Earth, you're going to have emergencies, medical emergencies. How do we handle that? Here you go to a hospital, and let's say you're having a heart attack or you got appendicitis. They have X-ray machines, they got MRI machines. They can look at your body and figure out what's going on and operate on you right away. Well, that's not the case going to the moon and Mars. First of all, the equipment that's used here on Earth for medical emergencies will not work in the space environment. And I'll say a little more about that later in my presentation. Next slide, please. All right, so I talked about first the human aspect. Now let's talk about technology. First tab, please. One of the big things is going to be the power. So first tab, please. So the first tab shows power. Power is going to be a major thing, a major challenge. Solar panels, they sometimes, they'll work if you're close to the sun. But if you get further away from the sun, they don't work as well, obviously, because of the radiant energy decreases as 1/r squared. And so power is going to be a major concern. We're looking at nuclear power as a way to power these systems for humans. Next tab, please. The other thing is robotics. Okay, so robotics is going to be a challenge as well. Tab, please. So that robotics, you're going to have robots that are operating in a deep space environment, and they're controlled by the human. Let's see. Next tab, please. All right, so those are robotics. Next tab, please. All right, so radiation. Okay, right there you see a radiation, what we call a radiation hardened computer control card. All right, these cards are designed for the deep space environment. Deep space has galactic radiation that can affect the performance of electronics. In fact, it can destroy electronics, especially commercial electronics. These particular devices, what you see there, are designed and built for the deep space environment. The problem is they're very expensive. And so we're going to have to figure out ways of designing systems that can handle deep space for a long period of time and that they don't cost as much. It becomes very costly to buy systems that are radiation hardened. I'll give you an example. Let's say, for example, a card that's used for graphics processing on a laptop that you use for, let's say, gaming or graphics processing can maybe cost 500 American dollars. For a radiation hardened computer graphics processing unit could run about $250,000 American dollars. Big change, big difference in cost. Next tab, please. All right, and then the other aspect, because these systems are becoming complicated, is the human-computer interface, and that's what I'm trying to show there, is that you got the human and the machine interacting with each other. That's going to be a challenge too in itself, again, because of the challenges of the human mind operating in deep space. You have the challenges of being depressed, you have the challenges of cognitive decline because of radiation, is that we're going to have to design systems that make it easy for the human to interact with the space system, and also importantly, dealing with human error. Next tab, please. Habitats. Just briefly, the habitat is going to have to be a place where they feel safe, a place where they have enough room to operate, to live and work, and to be alone. Sometimes they want to be alone. But it's a challenge because the bigger these things are, the harder it is to land. Next tab, please. Space communications. That's going to be a biggie. How can we communicate so far away from Earth and make it fast enough for them to communicate with loved ones? Okay, you just you can no longer like, for example, we're so accustomed to iPhones. You call your mom, you call your dad, and within a second you can be talking to them. That's not the case on the going to the deep space. It's going to take minutes. It's going to take 20 minutes, 30 minutes. You say, hello, mom. And then 20 minutes or 30 minutes later, they say, hello, son, or hello, daughter. It just doesn't work. All right. So we're going to have to develop better ways of communications. One option is doing optical communications. Next tab, please. All right. This is entry, descent, and landing, EDL. So the bigger the object, the harder it is to land on another planet. Because why is that? Because it's coming in at a very high rate of speed. And if you recall from your formulas, and if you've ever dealt with the physics, kinetic energy is 1/2 mass times the velocity squared. And so the larger the mass, the more kinetic energy it has. The more kinetic energy it has, the more it takes to blade off that kinetic energy so it can land on the surface of another planet more easily. That's going to be a major challenge because these components, like a habitat, the nuclear power systems, are going to be very heavy, and it's going to take a different way of landing them on another planet. Next tab, please. And of course, medical, the medical stuff. How are we going to develop an X-ray machine, MRI machine, a machine to do analysis, medical analysis of an astronaut on another planet that can handle the radiation that I talked about? Because again, the electronics may or may not be able to handle the radiation. Next tab, please. And then finally, the area of in situ resource utilization. There's a picture of a we call it a conceptual diagram of a in situ resource utilization station. So what is in situ resource utilization? Basically, it's a way of extracting stuff from another planet to useful for humans. For example, water. We're going to need a lot of water. We're talking about 800 and almost 1 million liters of water for a mission to Mars. And so how are we going to do that? We're going to need a way to extract water from another planet and create water. Well, it's going to take a lot of effort to do that. It's the things related to the mechanical systems, they're going to have to be reliable, that they can extract water for a long period of time. Going back to the moon, the regolith, or the sand, if you will, is very abrasive. It's kind of, like a friend of mine said, it's kind of like diamond. The sand is like pieces of cut up diamond, very sharp, very abrasive. They can ruin and destroy mechanical systems. So how are we going to do that? That's some of the things that we need to figure out over time. Next slide, please. And then there's the area of dealing with risk and hazards. All this that I mentioned are risks to the program, hazards, operating in another planet. This is something we have not done for a long period of time and for many, many months. Again, like I said, we only spent like 3 days on the moon back in the Apollo program. Now we're talking about months. So it's going to be a different, what we call paradigm. Next tab, please. So this is whole area of what we call risk mitigation and hazard mitigation. So down there at the bottom, what you see is something that a gentleman by the name of Dr. James Reason came up with, dealing with human error. And so I'll try to explain it. They call it the Swiss cheese model. And so, Swiss cheese basically is a piece of cheese, sometimes with holes in it. And so what he tried to explain is that we design systems with barriers, things to protect against a hazard, to protect against a risk. Like, for example, here I have requirements, I have design, I have testing, I have reviews, human factors engineering, I have safety, I have training, I have maintenance. But each one of these barriers to protect against a hazard is not perfect. And so the part that's not perfect is represented by a hole in the system. And so over here at the very far left, there's an event. They call it an initiator. And the initiator can be something that was done incorrectly. Maybe you pushed the wrong button. Maybe something failed at a time where you didn't expect it to fail. And then these barriers are supposed to protect against that. The top upper one, you see some kind of an initiator, and you see that red arrow being deflected by testing. What does that mean? Basically, like, for example, they develop a requirement, they design a system, a computer system or a mechanical system, but they never thought about a possibility of a hazard happening. And then during testing, they're testing the system, and they discover, oh my gosh, we just deflected a problem. And so that's what the human, but then there's cases where everything lines up perfectly and none of the barriers are able to protect against a hazard. A wrong switch is flipped. And so it goes through requirements. I missed it in requirements. I missed it in design. I missed it in testing. I missed it in design reviews. I missed human factors engineering, missed it. Safety missed it. Training missed it. Maintenance missed it. And what happens? A hazard occurs. Something blows up. Something comes apart. People die. All right. And that's basically what James Reason was trying to describe. So how do we do that for NASA? Next slide, please. And I'm just going to briefly cover these because there's a lot of information here. So what we do is that it's a four thing, pretty much at the very high level, systems engineering. Systems engineering is a methodical way of developing systems, very similar to the scientific method that I mentioned. It's a way of methodically developing systems. On the right-hand side, you see human systems integration. This is the part dealing with the human. How do we train the human for dealing with deep space. How do we design a habitat to accommodate humans? What kind of safety do we need to do to ensure that the humans are going to be safe on a mission? On the lower left-hand side, you see technology readiness level. There's going to be a lot of new technology that's going to be developed, and we got to mature that technology. And also we have to check to make sure that technology is maturing at the proper level to ensure that when everything starts coming together, that the readiness, what we call readiness of the technology, is there to support the mission. And then on the lower right-hand side, you see reliability and safety. I'm gonna say there's the next chart. We'll talk about that. But reliability and safety are going to be important. Keep in mind that reliability and safety are not the same thing. Something can be very reliable, but not safe. Something can be very safe, but not reliable. So it's a combination of those two that you work together to make them very optimized, if you will. Next chart, please. So let's talk a little bit more about reliability and safety. What tab, please? So there's first the hardware. The hardware part is, there's what they call it the bathtub curve. So hardware, whether it's a mechanical system or electronic system, basically has this bathtub curve, which basically says that early on is what occurs. We call it the burn-in phase, or the infant mortality, the early phases of hardware design. In other words, these parts are built, but something was done incorrectly and they fail. But if you use a system for a long period of time, or components for a long period of time, you're basically have no failures for a long period of time until it starts getting too old. And then the wear out phase at the very right part of the system is where it starts to fail. And because of that, you can develop mathematical models to predict when things are going to go wrong. So how do we test for this stuff? Well, we do best design practices, and I won't get into that in this presentation, but we deal with how we design reliably systems, whether electronic systems or mechanical systems. Testing, we do a lot of testing as well. Next tab, please. And then there's software. Software does not fail like hardware because software is just code. It's not physical things, okay? So software kind of behaves like a sawtooth. And so what that diagram is showing is that at the very left-hand corner of the diagram is where you have a lot of errors, but over time, you're able to get rid of those errors until there's a minimal failure rate of the software. And you keep doing this over and over again. So how do we find those errors? We do that through coding practices, through testing. We do different kinds of testing, especially in the space program with humans. We do unit testing. We do integration testing. We do performance testing, and we do regression testing. Regression testing is basically testing that's being done on software that's been modified a little bit, and we want to make sure that that modification didn't cause any problems. Next tab, please. Okay, and then we designed to make sure that a optimized design factors the human, the hardware, software, and the task. We're trying to match the task to the hardware system. We're trying to match the human to the task. Sometimes the human may not be the right person to do the task. Maybe it's a computer that has to be done. And then the human to the hardware system, we have to make sure that the human is able to operate the system. Are the switches big enough? Is the push button big enough, for the astronaut to punch it, not only with a bare hand, but also when he or she has a extra vehicle activity glove to punch that. Next tab, please. And then we have hazard analysis. We do a lot of hazard analysis. What if this fails? Okay, if this fails, how are we going to control that failure? And then how are we going to verify that failure has been controlled? That's part of hazard analysis. I can tell you that NASA spends a lot of time in that area. Next tab, please. FEMA, failure modes and effects analysis. That's basically looking at what if. Notice I keep saying what if. We do a lot of what ifs. What if this fails? What if that fails? That's a lot of thinking involved in terms of what can go wrong. We spend a lot of time in that because we don't know everything. And so we try to get as much as we can in terms of identifying where the risks are, where the hazards are. Failure modes and effects analysis is basically to try to figure out what can go wrong with the hardware, what can go wrong with the software, what can go wrong with the hardware and the software, what can go wrong with the hardware, the software, with the human, what can go wrong with the hardware, the software, the human, and the system. Different opportunities there. Next tab, please. And then finally, the human. Okay, the human, we're not perfect. From day to day, our mentality is much different. So we can have all kinds of errors related to slip of action. Slip of action is, oh man, I know how to operate the system, but I forgot. Today was not a good day. I wasn't feeling well. My one of my family members passed away. I'm just not, I'm depressed. Things are not working for him, and so they did the wrong thing to operate the system. And then there's the mistake related to learning a new system, and that's rule-based errors, knowledge-based errors, and that's something that we train astronauts for years before they actually go into space. This is part of human systems integration. In other words, getting the human, treating the human equally, just like a piece of hardware and software, to making sure that we've identified all possibilities. Next slide, please. Okay, so I'm just going to summarize everything that I talked about, because what you're seeing here is the total system development effort. All right, you have systems engineering process at the bottom, basically developing requirements, technical solutions, development, testing, but then you also have the human part, the human-centered part, the human-centered planning. How are we going to plan for human testing? Understand the user. How's the user going to be used in the environment? How are we going to design a system that's going to work with systems engineering to produce the right system for the human? And then how are we going to test this to ensure that the human is correctly integrated into the system? And then that error is basically the evolution over time of the optimized system. Keep in mind that the performance of the system is the performance of the hardware software times the performance of the human. Okay, because it's times, that means that either one of those is not good, the total performance is not going to be good. And so that's why we're doing things like matching the human to the task, to the design, and then we're doing all kinds of testing with the human. Workload, we're doing usability. How well do the astronauts like this system? Analysis, we're doing a lot of analysis as well. Next slide, please. And then final conclusions. Next slide, please. Click. So, we're going to go back to the moon, and in the moon, there's going to be a lot of challenges. Next tab, please. So, we're going to have, we're going to go to the moon to live and learn on another planet. It's going to be a catalyst for technology innovation. There's going to be a lot of innovation involved with going back to the moon. Next tab, please. And then we're going to get commercialization. We're going to get commercial companies involved. We're going to get other countries involved too as well. That's going to be important. Next tab, please. And then finally, eventually, we're going to go to the Mars. Mars is going to be our major challenge. Next tab, please. And so we're gonna search for life. Humans do a better job than machines in learning to understand if there's life or not. We tend to be more creative, obviously, than machines. That's one of the advantages of having humans in space. Mars climate change. They keep talking about Earth climate changes, right? Well, Mars has a climate change. It's been changing over the years. In fact, it lost its atmosphere. A lot of things have happened to Mars, and there were no humans on board. It just happens. It just happens. And so we need to understand that, because if Mars did not have any oil industries or anything like that, and yet the climate is changing, what does that say about Earth? Okay, so maybe Earth is destined for that regardless of what we do. It's hard to say. And then, of course, space settlement. We need to understand what's it going to take to start settling humans in other worlds. I think eventually that's what's going to help us keep humankind alive in the universe one day, when Earth is no longer. Eventually, Earth is going to die out, just simply because the sun is going to die. The sun's going to die. It's going to engulf a lot of planets, including the Earth. And so hopefully that's a few billion years from now. Hopefully by then we've evolved where we can go to other planets and get away from Earth before it's destroyed. And I think that was my last slide. And at this point in time, I think I still have about maybe 7-8 minutes for questions, if there's any. Thank you.
Thank you, sir. We take one by one. Oppo A52.
Hello, sir. Good evening, sir.
Yes.
Sir, I have a doubt. Sir, what type of materials used to make a space electronics, sir?
I'm sorry, can you repeat the question?
Sir, what type of materials used to build a space electronics?
What kind of electronics we use?
Sir, no. What type of material to use build electronics, sir?
What kind of materials we use for electronics?
Yes, sir. Yes, sir.
Well, most electronics are made out of silicon base. And so silicon has a certain atomic structure. And of course, anything with an atomic structure is basically susceptible to being hit by radiation particles. And so those radiation particles, basically, if you think about billiards or pool, is that a radiation particle will hit a lattice structure on a electronic component, and then that lattice structure is basically scattered. It hits it like a billiard, and it basically causes those electrons, or protons to spread out into different parts of the silicon. And so imagine what happens when you're running a program, and then all of a sudden this thing hits a part of the electronics that's operating a instruction, and it just changes the instruction. It causes some hazards, and those are the things that we have to be aware of. So, we're using silicon right now because as we've been using it for years, and so it's a challenge. It's a challenge with radiation effects, more so for commercial products. Commercial products are very dense in electronics and makes it more susceptible to radiation effects.
Sir, I have one more doubt. Sir, how tardigrades can survive on space, sir?
Hello, sir.
Hello?
Hello.
Yeah, I'm just seeing that there's some questions on chat. So I guess the moderator, it's your call as to, you want me to try to answer the questions on chat or the ones that are live?
Sir, at end we take chat questions, sir. We take questions from the students, sir.
Okay, there's a question related to living on other planets, possible next 100 years. What will the cost of living, and will it be possible for the general public? Yeah, I don't know, 100 years, right now we're talking about going to Mars in 2035 or so. And so, I would hope by by the 2100, that we know how to work or live and work on another planet. But it's going to take a while before we start living and working on another planet as a general public. I don't think we're ready to send the general public. I know SpaceX is trying to send 100 people to Mars, but it's just not doable, in my personal opinion. And the cost, very expensive, uh, very expensive. Somebody's asking about the Apollo space program. There's a lot of information about the Apollo space program. I encourage you to read up on it. There's a lot of information on the internet about it, but it was the first time we went back to the moon, and we had a total of 12 astronauts. I'm very fortunate to have met a few of them that walked on the moon. There were only 12 that walked on the moon. The last one was Gene Cernan on Apollo 17. He left a plaque saying that one day we'll come back, and I'm hoping that that comes true. There's a question about evaluation skills used for usability evaluation. Okay, so that's part of human factors, and there's questions that are asked to the human that's using the system about, what were their challenges, what were their thoughts, there's a series of questions. It's very methodical, and when they come up with a score, and there's a score, and I'm trying to remember a score of something like 4 or better is good. Anything less than 4 is not good, and so they have to figure out how to improve that. Same thing with workload. There's a scale for workload to figure out. This system is very intensive in terms of workload. We need to start figuring ways to make it more simple for the human. So it's very methodical. This is the area of human factors engineering. Not necessarily, engineers per se, but they basically, human factors folks understand the human. They understand the limitations, the capabilities of the human for operating systems. And that becomes very critical. You can design a hardware and software system that's perfect, no errors whatsoever, but a human that doesn't understand it can fail the system just simply because he or she didn't understand how it operated. Can we use centrifugal force to create artificial gravity? We can, but it's not a simple problem. You're talking about a mechanical system rotating at a certain rate. Well, mechanical systems fail. They can fail. And so how you build a reliable system, especially going in space, that could potentially be hit by meteorites and damage the rotating system, it's not a simple problem. But yeah, I mean, they've been talking about artificial gravity for years, and they're still not a proven design that's very reliable. So they're still working on it. There's talk about heat shields to avoid solar flares. You can to some extent, but solar flares, you got radiant energy, and you also have high energy protons, and so the shielding can get very heavy. And so the thing about weight in space travel is that the more it weighs, the more expensive it is to launch into space. So there's what we call a trade-off between weight and the effectiveness of the system for specific application. That's part of systems engineering. That's what systems engineers do. They're trying to optimize a system. You're looking at trading off pros and cons of different approaches. You just can't do one solution. You have to look at the pros and cons of each solution. You have to look at, is this going to meet the requirement? And so is it going to stay within cost and schedule? Let's see, which courses should I take joining NASA? Okay, so let me just share with you guys, sharing with that, joining NASA. So NASA is made up of government and contractors. I'm a government employee. I work for the United States of America agency called NASA, National Aeronautics and Space Administration. As a government employee, I had to be first a U.S. citizen. I had to show proof of being a U.S. citizen. And then they do background investigations to make sure that you are a U.S. citizen. And then there's the contractors like Lockheed Martin, Boeing, Northrop Grumman, all these contractors that support NASA. They usually hire people that have a green card. And green cards are kind of like an intermediate step for a foreigner that comes from another country to want to work in the United States. And it has to be something related to STEM. And there's more details. I'm not an expert in that. I can't tell you how many times people ask me, how can I come work for NASA? I'm not an expert in that. I'm just telling you what little I know. You really need to want to talk to NASA's, the United States of America Immigration and Naturalizations Organization. They'll give you more information about that. All right, I think I'm about 2 minutes over. Maybe one more question.
Sir, some students are waiting, sir. They want to ask questions. Panindra?
I'll take one question from somebody. Geez, I don't know who. Somebody,
Pani?
Hello, sir.
Yeah. Okay.
Yeah, sir, can we use transducers to produce electricity if we go to Mars or Moon? We can place it under our flooring, and because of the pressure, we can get electricity, right? Instead of as you said, instead of the solar energy, we can use this transducer to create electrical energy, right?
It's a possibility, but keep in mind we're talking about somewhere in the vicinity of 75,000 watts of power. Okay, this is a huge amount of power that's necessary, and solar panels may or may not work on the moon because especially where we're going to the dark side. We're not going to get a lot of sunlight. Going to Mars, the sun intensity is very minimal. Looking at different options. Right now, the trade studies are looking at nuclear power energy, but nuclear power energy has its issues. Okay, so for example, taking a nuclear power plant to another planet, what happens if it blows up? What's going to happen? You have to look at safety issues. This is part of systems engineering. You just don't come up with a solution. You have to look at what ifs. I keep saying what if this happens? What if that happens? What if this goes wrong? What if that goes wrong? We're always looking at these possibilities.
And also, sir, are there any plans going on for the space mining, like if you use any asteroids to mine for, as you said,
Yes.
we need water for the Mars and all. Like we can use our materials to construct on the buildings on Mars or Moon.
Yeah, there's contracts being let out for doing asteroid mining, but they're very right now is very preliminary. There's different things called optical mining. For basically an asteroid is captured and they mine that asteroid. They capture the material from that asteroid and send it back to the Earth. But we're talking years of doing that. I mean, you got to capture an asteroid that's 55 million miles away. It's going to be a while before it comes back to Earth. And so commercial companies are in the business of making money. And if they're not going to get their return on money very quickly, they're going to say, forget it. I'm not interested. So we have to find better ways of doing that. Okay, so I think I need to get, I think unfortunately, I'm out of time. So maybe one possibility is the coordinator can send me questions and I'll try to answer them and then get them back to you guys. But at this point, okay. I gotta get ready for another meeting.
Sir, now we are going to end the program. If any questions, you can text me in a creative group. Giridhar sir. Giridhar sir.
Hello. Is this audible?
Yes, sir. You can go ahead.
Okay, okay. Really, good evening, everyone. It has been such an honor to be a part of this wonderful, prestigious talk on human space flight challenges to the moon and Mars. Honorable Chief Guest, Mr. George Salazar, sir, respected dignitaries, and all the participants. It is such an honor for me to get the opportunity to thank you all the dignitaries. On behalf of our creative team, I would like to express my gratitude to all esteemed delegates of this talk for the presence and to make this prestigious talk a great success. I extend my gratitude to our honorable chief guest, Mr. George Salazar, sir, to take out time from his busy schedule to grace this talk. Thank you, sir, for inspiring and encouraging us with your words on this special talk. Actually, we got a lot of information about the space flight. Thank you so much, sir. And a special thank you, sir. And a special thanks to Sri Krishna Chaitanya, sir, the lecturer in mathematics, Turvekere, for providing immense support to make this talk successful. And the main on behalf of our creative team, I extend a really hearty vote of thanks to Vice Chancellor Sri S.K. Pandey sir, Raipur, for your presence in this talk, sir. Thank you, Roy sir. And I must thank the organizing team, that is Sri Srinath sir, Chief Patron, Creative Team, and ISRO scientist. Thank you, Srinath sir. And a big thank you to Supriya ma'am, Chief Executive Creative Team, for our efforts towards this talk. And I may like to express our sincere thanks to all the dignitaries who are participated in this talk. And I wish all to express my gratitude to our young students, in future the nation builders, who are participated in this talk. And thank you one and all, and thank you very much. Thank you, Supriya ma'am.
Thank you, George, for your wonderful time with us. It's very memorable for us for this event. Thank you very much, sir.
My pleasure. Thank you for having me. And I wish you all a good rest of the day, and y'all take care.
I request everyone to switch on your videos. We can take one photo with us, sir. 1 minute.
Oh, yeah.
Everyone.
Yeah. All right.
Yes. Yes, thank you, everyone. Sir, just I want to show you. There is one Ganesh Kumar is there. You can see him in a video. He is with so many students, childrens. Just I bringing some notice to you.
Okay.
Thank you, sir. Just I am